Hi, my name is Sohyun, and thank you so much for coming to my session. Um, a brief introduction of myself. I just finished my bachelor's course in sound engineering at University of West London, and I'm currently just started as a uh, um, master's student life in sound and music computing, Queen Mary University of London. I'm a amateur pianist, and very luckily, thankfully, I've been here in ADC for the last year and the year before as a diversity scholarship recipient. And this year, I'm giving my first talk, and I've been participated in the peer-to-peer C++ study group Dynamic Cast. I want to talk a little background on this project behind this talk. So actually, the topic on this talk is a virtual analog modeling, which is convert your analog audio units into digital signal processor. And this topic was actually the topic for my bachelor's final project. And last year, in this season, I decided to do some virtual analog modeling, and I needed to find some resource myself. And as I told before, I attended ADC 23 last year in London and tried to find some talks related to this topic. And I remember a few of great talks. I remember Jordan Evans modeled the Roland audio unit, and Jatin Chaudhry, not even the last year, from several years before, he gave a lot of good review talk on this topic. And I also met Abhishek Shivakumar, who's a CEO of the real-time audio plugin company called Quillio. And I also met Dr. Eric Tarr. I went to his session, and after his session, I just came up to him and I was like, "Hi, my name is Sohyun. I want to do some virtual analog modeling, and I don't know how to." I think it's quite a weird approach, but he was thankfully offered his private lecture series on YouTube. So that was my kind of basis resource for conducting my project. So I would like to acknowledge that this talk is indebted to people I met in ADC. Okay, so through this session, what I aim to share is a simple yet concrete examples for beginners or newcomers to virtual analog modeling, especially circuit modeling. And I want to clarify some confusing terminologies in this field. When I started to this project, I needed to have some time to know about the terminologies around here. And also, I want to share the fun of understanding the electronic circuits, which gives us a very amazing sound. So here's a repository. The thing is, in this repository there's a written report for both theoretical part and all the calculations for the session, because I've just found that the theory for doing circuit modeling is not very small, and dealing with every single line of calculations are impossible, I think. So please check out the report and the whole repository. And if you want to see something in more detail, and feel free to contact me if there is something some unclear part, I'll be happy to find out some solutions together. Okay, and let's get started. What is virtual analog modeling or VA modeling? Is to create your a digital signal processor which emulate the electrical behavior of your reference circuit. So analog system is a system that processes continuous input and output signal that vary over time. And the digital system is a system processes discrete input and output signal at specific intervals over time. And I think you all know these intervals depend on sampling rate. It's our period. The analog system we can consider is like a guitar pedal or every audio units like reverb units, or there's many more. And it can be drum machines, and also it can be analog synthesizers. And the digital system can be any digital signal processing script. So for example, MATLAB script or Python script, C++, whatever. And it can be a plugin. I think this is a guitar rig from the native instrument. And the digital system for VA modeling can be also neural network. So, I mean, the trained neural network. As I remember correctly, this guitar rigs from native instrument is modeled with this neural network method. So yes, again, the creating VA modeling is to create a digital signal processor that mimics the electrical behavior of a reference circuit. And here's the terminology of physical modeling, which makes me so confused when I just started this project. Physical modeling is absolutely different from VA modeling. Physical modeling is to emulate the behavior of sound-producing objects in the real world. So, for example, the acoustic piano, acoustic guitar, acoustic violins, and so on. If you're a keyboardist or pianist and you like to use some virtual instrument, you must have been heard of Pianotech. It's very famous one. As I know, this one is modeled with a physical modeling method. Introduction to the task. We will do in this session the VA modeling of the MXR Distortion plus guitar pedal based on a circuit analysis method, which is called white box modeling method. Circuit analysis methods for analyzing individual individual components in the circuit and the complete circuit. We will model by sub-circuits, and we will implement the digital signal processing using Python in Google Colab, or yeah. And finally, we're going to do some listening test. So we have an audio file, and the audio file passed through our DSP, the VA model one, and the same audio file through the real pedal I recorded myself. Okay, so this is the pedal. This is our reference circuit for today's session. It's called the Distortion Plus. There's some information of this pedals, the brief history, but I know you want to just listen to it. Sounds nice, right? I just want to ask you, anyone have used this guitar pedal? Or oh, really? Yeah, yeah, cool. Yeah, this is our reference circuit for today. So this is the left one. The picture is what I pictured myself. Is when you open the box, the yellow box, is the real component in the pedal, and the figure on the right side is the schematic of the whole circuit. Actually, there's some helpful prerequisite knowledge for doing circuit analysis, circuit modeling, virtual analog modeling. First of all, is about voltage and current. So voltage is also called potential difference. It's a pressure of electricity which pushes electrons from a point of higher potential to a point of lower potential, and it's measured in volts. The symbol is V, the capital letter B. The current is the amount of electron flown in a circuit, and it's measured in amperes. And we also need to look at some components which is consisting of our circuit. Can I just briefly back to the overall schematics? It can be seen a bit complicated, but actually there's only 1, 2, 3, 4, 5 components here. It's resistor, capacitors, diode, operational amplifiers, and potentiometer. We will go one by one. So resistors, the middle one is the schematic expression of the resistor. It limits the amount of current and divide voltage in a circuit, acting like a bottleneck, and it's measured in ohms. And this is capacitors. Capacitors can store and release electrical energy. The current through a capacitor and voltage across it keep changing, not like a resistor, and it's measured in farads. And here's a operational amplifier. Is a high gain voltage amplifier. And if you see the schematic, there's two input terminal, which is marked plus and minus. The plus one is a non-inverting input terminals, and the minus one is a inverting input terminal. The key rules for operational amplifier, there's two rules. First of all, if there's a feedback loop in a circuit, the feedback loop is actually the loop connected the inverting input terminal and the output part. So if there's a feedback loop in the circuit, the voltages at the two terminal, the inverting input terminal and non-inverting input terminal, are always equal. And the second rule is no current flows into the two input terminals. And diode is a polarized component, so we should mark which part is anode, which is cathode. Diode current flows in one direction, only in one direction, from the anode to the cathode, and blocking reverse flow. And finally, the potentiometer. It's called a variable resistor. This is a knob in our pedal. Potentiometers adjust resistance within a given range to control voltage and current. So if you have a potentiometer valued like 1,000 ohm, you can adjust it from 0 ohm to 1,000 ohm. Yeah, we've looked at some components, and here's some laws, Kirchhoff laws. The first of all is Kirchhoff's current law, and the second one is Kirchhoff's voltage law. I want to talk about node first. The node is connection between circuit components. And for Kirchhoff's current law, the total current entering this node in an electrical circuit is equal to the total current leaving, like flowing out the node. And the Kirchhoff voltage law is the sum of all voltages around any closed loop in an electrical circuit is equal to 0. And a bit of calculus, this basic concept will be very helpful to doing virtual analog modeling. So derivative is a rate of change at a specific moment, and it's also can seen as a slope. And the differentiation is a process to calculate the derivatives, the rate of change or slope for a specific function. And integration is like an opposite concept. Integration is a process to calculate the accumulated total. We're going to use this all the concepts I've just addressed in the real modeling part. Okay, so there's some circuit analysis method. It's very important because when you do the VA modeling with a circuit analysis method, I think the most important thing is understanding the circuit. So here's several things I want to share. The first of all is a nodal voltage analysis method. So this is like you can label a node in the circuit. So you can see it in this figure, like VA, VB, VC. This is all the labeled node. And it's with an unknown voltage value. You don't know what values of the voltage in this node. But you can formulate equations using Kirchhoff current law or Kirchhoff voltage law we just saw. And this example is about the Kirchhoff current law, which is you can see the node VB, and the current is coming to the VB, and then coming out through the resistor this way. So the equation here, VA minus VB over 10, means did we talk about Ohm's law yet? No? Sorry. This VA minus VB over 10 is, in Ohm's law, it's the current flowing through the resistors. So we can formulate using nodal voltage analysis. And why do we use this? Using nodal voltage analysis, we can further find out a mathematical expression that defines the relationship between input and output, and known as a transfer function. And this transfer function is actually everything we want to know to do the model or analog circuit. And this transfer function allows us to apply a even discrete input to a system originally designed for continuous analog signals. Here's Ohm's law. So this is for resistors. So Ohm's law expresses the relationship between voltage, current, and resistance in a circuit. So V equals I times R. V is the voltage, I is the current, and R is the resistance. I think this is the most simple and my favorite law in the world because it's simple. But what about capacitor? It's a totally different story. It's not simple. Well, finding the voltage across and current through a capacitor is not as simple as with a resistor. Why? Because a capacitor is dynamic component with time-varying voltage and current. So, with respect to resistor, if you want to find current through the resistor or voltage across the resistor, it's always same. It's the value never changed over time. It's a fixed value. But capacitor is different. It's always changing. And as you see, the formula is not pretty. These equations represent the voltage across and the current through the capacitor in an analog system, so over continuous time. Equation 1 shows the voltage across the capacitor is equal to the integral of the current flowing through the capacitor and divided by the capacitance. And equation 2 means the current through the capacitor is equal to the rate of change of the voltage multiplied by the capacitance. As you see, actually, this both two formula is the same one. It's just expressed as with respect to voltage or with respect to the current. As I've mentioned before, these equations are for the analog system. But what we want to know is the equations for discrete system, because we want to create a digital signal processor. Not over time, but by each discrete sample, so that we can use the equations for achieve our VA modeling job. And here, this is called a discrete Kirchhoff substitutions on capacitor. I will go through the principle behind of this method, but I want to share first. When you in our work, in our process for doing virtual analog modeling, when you see one capacitor in your circuit, we will substitute it with one resistor and one reversed current source in a parallel configuration. This actually makes things easy to find the voltage and current with respect to a capacitor. As you see before, if you want to find the voltage or current through the capacitor, the formula is not pretty. But if this substitution makes sense, if this substitution is true, when you want to find the voltage across the capacitor, you can just find the voltage across the resistor, because this resistor and the reversed current source is configured in a parallel circuit. So in parallel circuit, the voltage across every point is all the same. So as we see the Ohm's law, to calculate the voltage across resistor is very simple. So it's happy things, and and yeah, as same as the current. The current flowing through the resistor is very easy. Also, we can use Ohm's law, and the reverse current source, we can just subtract it. And yeah, so let's see how could we substitute like this, and what values we could assign for resistor and current source, because we don't know yet what the value of the resistor and what's the value of the reverse current source yet. So here's the principles behind the decay substitution for capacitors. With this graph, with respect to, this graph, let's think the x-axis as a continuous time. But we marked x0, x1, x2, x3. This is our discrete point. So this is a discrete point in time. So yeah, and if we think of the respect to the discrete time point x2, the voltage across the capacitor is the area under the function's curve up to the x2. Why? Because of the formula, the first formula, voltage across the capacitor is using the integration. So the voltage across the capacitor is to calculate the area under the function's curves up to the x2. And in the opposite, the current flowing through the capacitor is a rate of change of voltage multiplied by capacitance, as we see in the equation 2. We can express this like this. So equation 1 represents the current flowing through the capacitor at a discrete time point x2 as the difference between the accumulated voltage up to x3 and that up to x2. So can I move this? So this area and subtract this one. So only this part can be current flowing through the capacitor. And equation 2 is the same as equation 1, but we now use a discrete time. So equation 2 substitutes equation 1 into discrete time voltage change equation, reformulating it for the discrete time signals n and n minus 1. So V of discrete signal n is the voltage when the nth signal is your input, and V of n minus 1 is the previous discrete signal. Sorry for so much math. So we just see the equation 1 using the discrete signal n and n minus 1 expression, and reorganizing this equation 1 for the current I flowing through the nth discrete signal results in equation 2. So just rearranging this with respect to IN. And then in the equation 2, you can see there's a term related to the previous discrete signal n minus 1. And it can be grouped together and expressed as x n minus 1. Why? Because this expression n minus 1 is a contribution from the previous discrete signal. So rewriting this equation 2 using the state value. So we group this n minus 1 terms into one term x of n minus 1, and we call this state value. And rewriting equation 2 using this state value leads to equation 3. And this equation represents the current flowing through the capacitor when the discrete signal n is the input. And it can be visualized as shown in the figure on the right side. So the right side figure is about the equation 3 because it's the left-hand side is I, so it's all about the current, and the 2c over Ts times V of n can be expressed as a forward-directed current source, and our state value x of n minus 1 can be represented as a backward, so reversed current source, because there's minus in between the term. That's why it's configured reversed direct. So here we've already convert our capacitor in our circuit into one forward direction current source and the other reverse direction current source in a parallel configuration. But we have one stage more to do. When you see the equation 2, the V of n times 2c over Ts is the expression for the forward direction current source. And when you see this, you can remind of the Ohm's law. So V times something equal I. And this is the current source, and so this is current. And from here, we can interpret 2c over Ts as a 1 over R because of Ohm's law. And if we flip away, we can express R equal Ts over 2c. So finally, we can substitute one capacitor in our circuit into one resistance, which has the value of Ts. Ts is a period, Ts over 2c, and one reversed direction current source, which is our state value, x of n minus 1. And this is configured in a parallel circuit. And we actually need state update equations because our state value, x of n minus 1, is need to update every time the sample by sample signal processing is going. The equation 1 is what we've already obtained. It's about our state value, x of n minus 1. And the second value, we changed the n minus 1 in equation 1 into n, because it's n minus... in equation 1, you can change all the n minus 1 into n, so it's the same thing. And equation 3 is we've already obtained here in equation 2. And we can go back to equation 2. There's the I of n term at the end, and we can substitute with the equation 3. Then we can calculate, we can obtain the state update equation for x of n. So x of n minus 1 is the state value because it's from the previous discrete signal, but every time the signal processing is going further sample by sample, your state value should be from x of n minus 1 to x of n. So this is the state update equation. So yeah, it was a lot, but there's 4 takeaways with respect to capacitor. So first of all, we can use the equation for achieving current flowing through the capacitor over time, but we also obtain the formula, which is current flowing through the capacitor, but not over time t, but by discrete time sample n. And the second thing is, whenever we see the capacitor in our circuit, we want to substitute it with one resistor and one reverse direction current source in a parallel configuration. And third, the second, the value of resistor here is a period over 2c, and the state value, x of n minus 1, this is a signal affected from the previous signal. And then we finally achieve the formula for a state update equation. And then about diodes, now we can go to diodes. So when you see the schematic, the two diode is configured, one diode in this direction and the other one is the opposite direction. We can call this back-to-back configuration. And one diode conducts current when the signal flows in the positive direction, while the other diode conducts when the signal flows in the negative direction. And there's one feature of a diode is a clipping voltage. It's usually 0.7 volts. When your input signal is below this clipping voltage, it passes through unaffected. So your signal is not affected by this diode. The diode is not activated. However, if your signal, your input signal exceeds this clipping voltage, this 0.7 volt, current flows through the diode and limiting the signal at the 0.7 voltage threshold and creating a clipping effect. And this results in a distorted sound in the pedal, where the fundamental pitch is preserved, so pitch is never changed, while additional harmonics are introduced and giving a richer and more aggressive tone. And we also need to find the current through and voltage across this diode. And there's a equation called Shockley diode equation. We can just take it as a granted. The first equation is about the current flowing through the one diode, but the second equation is the current flowing through the back-to-back configuration of diode. So we're going to use this one because this schematic is our schematic of MXR Distortion Plus. And also, for diodes, there are some parameters and coefficient depending on the material of diodes. In our case, in the reference circuit, there's a germanium diodes, and germanium diodes parameters and coefficients is like in a code. So the saturation current of germanium diode is 10 to the power of -6, so 1 micro. And the thermal voltage is 26 millivolt, and the emission coefficient is usually between 1.5 to 2. And actually, these parameters and coefficients, we can just take it for granted. We will use these values in our code. But here, if you need to set this equation with respect to VD, so the voltage across the diode, which is the voltage across a pair of diodes, it's not possible because, as you see in the equation 2, VD is inside the hyperbolic sine function. And to tackle this, we need a method called Newton-Raphson. Let's take a look. So, Newton-Raphson method, to solve for VD in this second equation, the equation cannot be directly solved because VD is inside this hyperbolic sine function. And to solve this, to address this, the equation is rearranged so that all terms are on one side and call this function f of VD. So all the terms are on one side, so the other side is going to be a 0. And our goal is to find the value of VD that makes this function f of VD equal 0. And Newton-Raphson method starts with arbitrary point as an initial guess, because we don't know where is the root. And then the slope f of VD of the function at the initial point is calculated, and then check where the slope intersects the x-axis, and then check again the function, this f of VD's value. And if it's not 0, this is not the root we found. So we repeat this process over and over until we find the root. Should I? Yeah. And also we need a state update equation for Newton-Raphson equation. So here, if x0 is our initial guess for VD, and x1 is our next guess, so we assume our first guess is failed, you can set the equation as equation 1 for expressing the slope of the original function. And if you rearrange this equation 1 with respect to next guess x1, this equation 2 becomes the state update equation for Newton-Raphson iteration. And every time you fail to find the root, which is the VD's value to make the function 0, you want to update the newly guessed VD. So yeah, this is the circuit analysis method we've looking. And this is the modeling part. I know we have run out of time, but don't worry, I will only explain the process of it. So this is our op-amp stage. This is our op-amp stage through the whole circuit. And as you see, the right side of schematic is the decay substitution circuit. So I substitute every single capacitor into one resistor and one reversed directional current source. What we aim to find is set up two equations for Vx, then eliminated it and derive the transfer function that represent the relationship between Vin and Vout. So there's several processes, two branches of the input section. At the non-inverting input node Vx and using Kirchhoff current law, the following equation is derived based on the fact that the current flowing into Vx from Vin is equal to the current flowing out of Vs through R8. And in the potentiometer section, the current IC existing the node Vx exiting the node Vx is calculated using the fact that the current is the same throughout the segment, along with the equations for the current flowing through the resistor and capacitor. And feedback loop session, also we use KCL, Kirchhoff current law, with respect to node Vx with the obtained current value from the previous process, and find the equation for Vx expressed with Vout and the component values. So with this, from process 1 to process 3, we obtain the equation which is describing the electrical behavior of operational op-amp stage circuit, not over a continuous time, but by a discrete time. So the two equations for Vx obtained in process 1 and process 3 are formed the simultaneous equation. And as we told before, after Vx is eliminated, then the transfer function of this op-amp stage is obtained by solving the remaining equations for Vout. So this is our transfer function of the op-amp stage. And this is the state update equation. The process to obtain this one, we've already covered it. And the clipping stage modeling, also I did the decay substitution circuit, substitute just only one capacitor into one resistor and one reversed direction current source. And here's, first, we use the nodal voltage analysis for the node VD using KCL. And second, we move all terms of the equation 1 to one side and express it as a function f of VD in terms of VD. And then we calculate the derivative of the function to determine the next guess for the Newton-Raphson equation. And the equation force is about the Newton-Raphson update equation. And we also using KCL to derive the transfer function for this clipping stage. And yes, that's it.
Please give a round of applause to Sohyun.
Thank
Go and
you.
find that.